Hi everyone, this is Rick, and here's yet another lecture on my series about comic book science and this aging of paper. And this time we'll talk about the effect of light on paper. We've already talked about acid and oxygen and other things, and now we're going to talk about photo stuff. So this is a branch of something called photochemistry, and photochemistry involves photons either initiating or sustaining a chemical reaction. And you won't see my face a whole lot in this one because I'm just going to talk on some of my notes, but I hope you enjoy. Take care. See you around. So today we're going to talk about photochemistry. Photochemistry is chemical reactions that are either initiated or sustained by light, meaning photo, right? Of course. And there are two laws that have something to do with this. One's called the Grotius-Draper law, and the other one's called, well, we'll just skip the other one. It's an Einstein thing. It was discovered in 1818 by Grotius, and then about 20 years later by Draper. And there's a little example I want to show you in this video here. Here's a photons transferred across a series of hydrogen bonds between hydronium atoms that's photoexcited. So you can see like a little video of it happening here. You kind of watch and get an idea of what's going on. So let's get this out of your way. In the following chemical equations, each symbol for an element stands for one atom. So you see Cl2 here, and that is two chlorines bonded together, and then it's excited. This means it's excited by a photon, and it turns to 2, and these should be Cl minuses really, but I just left the minus off. And the distinction is that it looks kind of like this. It looks like one Cl2, I'll draw it out here for you. It looks like a Cl is bonded to a Cl, a chlorine. And then, I guess it would actually be a double bond. But then it turns into two individual, actually I'll just draw them out, Cl minuses like that. That's the distinction between the little 2 on the subscript 2 and the 2 in the front. You're seeing two bonded together on the left as a reactant, and as a product you see them individually. So I'll go through and read my notes here. The symbol H nu may be read when a photon of light frequency, symbolized by the Greek letter nu, is absorbed. It gives this. That's what that means. So when you see this sort of a symbol of H nu, and H is Planck's constant, which is 6.6 times 10 to the minus 27 erg second times its ergs times second, and nu is expressed as reciprocal seconds. So that might be a little confusing to you. So Planck's constant is 6.6 times 10 to the minus 27, and it's erg times seconds, and that's Planck's constant. Looks like this. And nu looks like a V, but it's a nu. And nu is in reciprocal seconds. It's inverse seconds, we call it. That's what frequency is. So then you multiply erg seconds times 1 over seconds, and you just get ergs. You end up getting a unit of energy. So that's the neat point about that thing. And so what you'll see here is, like in this example, chlorine is excited by a photon of light, becomes two chloride ions. The chloride ions, and this is bugging me, I should have written the minus on these, reacts with hydrogen gas to form hydrogen, performs HCl, which is hydrochloric acid, and the other H+. The H+ then reacts with further Cl2s and makes more hydrochloric acid and Cl-, and that's a common reaction that would be written something like this. But it could go actually two separate ways. You could actually make two different products. That's why there's an or here. So it reads, some reactions may give two primary products. And so this is called acetal right here. This is called acetal. Acetal looks like this, incidentally. It's like that because it's an aldehyde. And so one thing you'll want to know is that an aldehyde is a terminal ketone. So it can be anything. This is an aldehyde because it's on the end, but one of those in the middle is called a ketone. So this is an aldehyde, and this is a ketone. And that's only because it's on the end and the ketone's in the middle. This is called, in either case, this group's called a carbonyl group. carbonyl group, a carbon double bonded to an oxygen. So that's something to note. So there are two parts of, remember, you probably already remember, there's two parts we're concerned with here when we're talking about paper. And then there's the cellulose and the lignin. Cellulose is good and strong, and this is the good stuff we want. Lignin is usually not so good and strong. And those are the two components in the paper. Usually we want the lignin to be removed, but in pulp paper and comic books we must consider it because it is still there. So we have, I wanted to show you that highly purified cellulose, which is, we'll go over the molecule of that in a minute, does not absorb light in the visible region at all. It doesn't, but it does absorb weakly in the ultraviolet region around 260 to 270 nanometers. So in the whole spectrum of light, this thing here, right here, we only see this little sliver. This is the visible region. It's from about 350 to 750 nanometers, right? Far left of that is the UV, and far right of that is infrared, and then it goes to microwave and then to radio waves. As they get longer, the wavelength gets longer and frequency gets lower. So as the wavelength gets shorter, it goes this way. We could go to UV, X-ray. These are higher. This is a really high energy. This is really low energy. So this won't hurt you on the right, it will on the left. And you see this little tiny sliver right here. So where does cellulose absorb? Now it doesn't absorb where you can see, so it doesn't really impact the color, right? That's because it is what did it say here? 260 to 270. So 260 to 270 is way down here in the UV. You can't see that. It's below what your eyes can make out. So, but it is reacting with the paper. You just can't see it. And it says strongly below 200 nanometers. So that's far down into there. So in addition, it has been observed that ultraviolet light emitted from a mercury lamp, just a regular lamp, this is an older research paper, will photodegrade cellulose with a formation of carboxyl groups, lowering the degree of polymerization. You may remember that we talked before about the DP, the degree of polymerization, or how strong the paper is and how polymerized it is, right? So how long those cellulose fibers are. And we want to get rid of lignin so that we can get those cellulose fibers lined up and polymerizing better, right? So that they're stronger. And lignin is not straight like this. It's kind of a mess. And so it interferes with that. And also the formation of carboxyl group. Now carboxyl group looks like this, right? And that messes it up because it breaks the chain and forms one of these groups. A number of degradation products include, I don't even know how to pronounce this. It's dialdehyde. So it's malondialdehyde is one of the groups that gets formed. It's like this one. I just thought I'd make a note of it. A variety of sugars and volatile and non-volatile acids. Volatile meaning it evaporates off the paper, which is why you want to keep your bags open a little bit. Higher intensity ultraviolet radiation will produce an even greater number of degradation products. So if you have more or higher frequency, you get UV light, you'll get even more degradation products, including carbon monoxide, CO2, and carbon dioxide, and H2, which is just hydrogen gas. Once degradation of cellulose product begins by direct exposure to UV light, new functional groups formed by the cellulose polymeric chain can exert an autocatalytic influence, behaving as new absorbing centers. Meaning that what will happen is the spots that are made, like if you make something like this, let's say it's like that, it actually is a new spot that'll take even more energy, and it gets even worse, is what it means. The presence of oxygen can lead to the formation of hydroperoxides during ultraviolet photolysis of cellulose. So these groups get formed quite a bit. Especially, I mean, there's some people that actually seriously put peroxide on their books, and then they hit it with UV light. So they're asking for trouble because they're going to be forming this stuff. The book will look whiter right away because you'll have killed some of the chromophores that make it look yellow, but you are definitely that book will not last very long if you do that. So I would be cautious. These hydroperoxides are decomposed readily by light and can form free radicals. Now, free radicals you don't want. Those little suckers are just little tiny electron-bearing groups that just tear through stuff. That can cause scission of the cellulose chain. Further oxidation can occur with the formation of carbonyl and carboxyl groups. So this is a carbonyl group here, and if you were to put like an OH in here, that would be a carboxyl group that forms when these hyperperoxides form. These form in the presence of, remember, oxygen and light, but if you intentionally put UV light on a book and you intentionally put peroxide in it, you're certainly going to form these. And it breaks the paper up, makes it very brittle. Degradation of cellulose by light can also occur indirectly by photosensitization, whereby impurities absorb light and light quanta and transfer their excitation energy to the cellulose chain, meaning that the fingerprints and dirt and other junk on there will actually absorb the UV light, and then they will have excess energy that they transfer to the paper. So that means indirect. Here's some examples. So here's cellulose right here on the left, right? Let's look at this guy. This is cellulose, and you put periodate on it, and then they're showing it. This looks the same here, but it's broken open. So you'll notice that this part is broken here, and you've got two of these carbonyl groups forming two aldehydes, and these are two. This is broken here and forming two carboxylates. So these are aldehydes here. Now, not only that, these are chromophoric, because now these guys have double bonds in them, and sometimes they're conjugated, meaning there's another one just 2 steps over or nearby, and they'll be yellow. And so this is a carboxylate. I'm not going to write that out. So it says oxidized cellulose, hemicellulose, lignin, metal ions, dyes, and extraneous materials are these things that could do that. Thus, paper can absorb both ultraviolet and visible light, leading to the degradation of cellulose chain and discoloration. So even if you have your book in a case, or something that's filtering out the UV light, the visible light will hurt the dyes and inks and fingerprints and things, and will cause these kind of problems. So you're not escaping. I would keep them in the dark as much as possible as the rule. I would not display them outside, especially where sunlight can hit them. Obviously, putting them in UV protective case will help, but it's not the cure. Let's see here. Studies on the yellowing of cotton cellulose upon aging also indicate a relationship between yellowing and aldehyde group content. Lignin, and we're talking about lignin, we're moving from cellulose to lignin, a very complex polymer based on phenylpropane building units, contains a number of chromophoric groups. Now, chromophoric means absorbs color. In our case, means turns yellow. That can absorb in the near ultraviolet and visible spectral region. This is an example of kind of what lignin looks like. This is like a sample. It doesn't look exactly like this. It can look like this. All the things that can happen to it are on the outside here. And here's another example of a lignin molecule. It's just nasty. It's not straight and even at all like cellulose is. And it's the wood. It's the pulp in wood pulp. It's the stuff that they remove from paper pulp to make paper stronger and better, and they don't remove it in comic books and newsprint. It makes it kind of brown and rough. Here are some examples of these chromophoric groups, and I'm talking about here in lignin. So we've got, this is one here. Now, where you see this kind of a group like that, where it's conjugated and also delocalized, you know that's going to be colorful. And depending on what these other groups are, it kind of changes the intensity of the color. But every time you see, man, look at this sucker. This one would be really deep yellow. So these kind of things form, and that's what makes them chromophoric. Those make them really yellow. So I'll just put like a yellow. So all these things are going to be super duper duper yellow as they get formed from lignin. And here's this process, right? So here's this, we have a biomass like a tree, especially. They even extract, they remove the lignin. Basically, they put it in a high pH solution to remove it from the cellulose, and then they use acid to drop the lignin out. And then what happens to it in the presence of light is that, like, this one here is broken. That's called scission. And then this went from like an alcohol. It oxidized up to an aldehyde. This is probably in the presence of oxygen. And that's what happens. This is this conjugation and the color changing. And if you want to see what frequency these different groups absorb at, they are absorbing in these regions. And as they start to get closer and closer to, visible, these things are pulling out the blues and looking more yellow, basically. So these are chromophoric structures in lignin that's been aging. Lignin in an excited state can act as a sensitizer too, inducing the degradation of cellulose. So basically, even the lignin can make not just lignin fall apart, which it always does, but it can also make the cellulose fall apart. As a result, comic books and other high-yield pulps that contain substantial amount of lignin turn yellow when continuously exposed to sunlight. The overall effect of light on paper products is to cause a degradation of the cellulose chain and a lowering in the degree of polymerization, which is that DP thing we talked about, the strength of the paper. At the same time, both light and atmospheric oxygen cause the formation of carboxyl groups. Remember carboxyl groups? Which generates more acidity in the paper. While cellulose in its pure state is relatively unaffected by natural sunlight, the presence of impurities such as lignin and metallic cations, and that's from the ink, and metallic cation just means like positively charged ions, which hurts the foxing too, will initiate photochemical reactions resulting in the degradation of the cellulose chain. These photoinduced reactions are enhanced by acidity, a high paper moisture content, and the presence of oxygen. So as we've been saying all along, acid, water, and O2 and light are our enemies. We don't want them anywhere around us. They're terrible stuff. So anyway, that's your lesson for today. I hope you enjoyed it. Well, how'd you like it? I hope you enjoyed that video. I was kind of wondering what to do next. I was thinking about doing foxing. I'm kind of running out of ideas. Maybe you guys have some ideas and stuff you'd like to see. I'm getting a little bored doing the same cleaning examples all the time. Kind of running out of ideas for stuff to teach. I mean, I guess I could probably think of something. But maybe you guys want to learn something else. Let me know. Obviously you know what to do. And anyway, I hope you like the videos, and I hope you learn something and come back for more in the future. Take care. All right, bye-bye. See ya.